Welcome back, Physics 30. This is FI2.4. So we looked at electric fields with the previous one. Now we look at magnets and magnetic fields. So we represent magnetic fields using magnetic field lines, which are similar to electric field lines. And then to draw the magnetic field pattern produced by iron filings sprinkled on paper placed over different arrangements of bar magnets. So the history of magnetism began thousands of years ago when the region of Asia Minor, known as Magnesia, rocks were found that could attract each other. These rocks were called magnets, named after, of course, the place of discovery. Not until the 19th century, however, was it seen that magnetism and electricity are closely related. A crucial discovery was that electric currents produce magnetic fields like magnets do. All kinds of practical devices depend upon magnetism, from compasses to motors, loudspeakers, computer memory, and electric generators. And we'll see that later on because there's an assignment near the end of this unit that involves you to look at some of these. Any magnet, whether it is in the shape of a bar or horseshoe, has two ends or faces called poles, which is where the magnetic effect is strongest. If a bar magnet is suspended from a fine thread, it is found that one pole of the magnet will always point towards north. It is not known for sure when this fact was discovered, but it is known that the Chinese were making use of it as an aid in navigation by the 11th century and perhaps earlier. This is the principle of how a compass works. A compass needle is simply a bar magnet which is supported at its center of gravity so that it can rotate freely. The pole of a freely suspended magnet that points toward the geographic north is called the north pole of the magnet. The other pole that points towards the south is called the south pole. So if we imagine it like this, a magnet, there's a north pole and a south pole, and it lines up with the Earth's magnetic field. It is a familiar observation that when two magnets are brought nearer one another, each exerts a force on the other. The force can either be attractive or repulsive and can be felt even when the magnets don't touch. So again, force at a distance. If the north pole of one bar magnet is brought near the north pole of a second, you can see that it is going to be repulsive. So it's almost like charges. Two negative charges would repel, or two positives repel. Same thing with the magnet. So here, like repels, opposite, of course, attracts. These results shown in the figure here and are reminiscent of course, electric charges. Very similar though, even though these are different concepts. So if you look at the next page, so unlike poles retract, but do not confuse them with, of course, electric charge because it is different. One important difference is that positive or negative electric charges can be isolated. So you can have something that's negative or something that's positive, but no matter how many times you cut a magnet in half, you always get a north and a south pole. Okay, so instead, two new magnets are produced when we cut it. Keep cutting it continuously. If the cutting operation is repeated, more magnets are produced, each with north and south pole. Physicists have searched for isolated single poles, but they have never been observed. So that's the one difference between magnets and electric charges. Besides iron, a few other materials such as cobalt, nickel, gadolinium, and some other of their oxides and alloys are strong magnetics. They are said to be ferromagnetic. Ferro coming from the Latin word for iron. Other materials show some slight magnetic effect, but it is very weak and be detected only with delicate instruments. Earlier we used the concept of electric fields surrounding an electric charge, and similar we can look at magnetic fields. The force one magnet exerts on another can be described as the interaction between one magnet and the magnetic field of the other. Just as we draw electric field lines, we can draw magnetic field lines. So, a couple of rules for that. The direction of the magnetic field is tangent to a field line at any point, and the number of lines, again, is proportional to how strong it is. The direction of the magnetic field at any given location can be defined as the direction that the north pole of a compass would point if it was there. So, if you recall with electric fields, to figure out which direction the electric field is, we put a small positive charge here. But for here, we look at which direction the compass needle would point if placed at that direction. So over here, now I can't remember on your diagram, well, I guess yours looks like mine. So you can see here, if this is north, or sorry, let's make this south, and then this is north. Kind of hard to see here, but if this is north and this is south, so field lines extend out from the South Pole and extend out from the North Pole, and then of course go from north to south. So the direction that the compass would point, as you can see, so the North Pole of all these compasses are pointing along that curved line. So they'd point away from north and towards south. So all these here are north poles, north poles, north poles, pointing towards the south. So that's kind of how we do that. So the figure on the right shows how thin iron filings, acting like little magnets themselves, reveal that the magnetic field lines by lining up with a compass needle. The magnetic field determined in this way for the field surrounding a bar magnet is shown on the right. I guess I had it reversed here, it doesn't matter. So if I drew the magnet like this, the north here, south here, so away from north and towards south on the outside. On the inside of the magnet, you could think of these curves continuing on and going towards north on the inside, but we always discuss the direction on the outside of the magnet, away from north and towards south. Notice that because of our definition, the lines always point out from the North Pole and in toward the South Pole of the magnet. The North Pole of magnetic compass needle is attracted to the South Pole. Magnetic field lines continue inside a magnet as shown. Magnetic field lines always form closed loop, unlike electric field lines that begin on positive and end on negative. So they continue on inside the magnet. Earth's magnetic field. So the Earth's magnetic field is shown below right and is thought to be produced by electric currents inside the Earth's molten iron outer core. The pattern of field lines is almost as though they were an imaginary bar magnet inside the Earth. So if we take a look here, it's very similar to what we have going on here. Now the interesting part here is if the North Pole of a compass points to the North Geographic Pole, that means that the inside of the Earth, it would be as if the south part of a magnet is at the top and the north at the bottom, because remember, the North Pole of a compass is the North Pole of a magnet, and if it's attracted to the North Geographic Pole, the North Geographic Pole must actually be a south pole of a bar magnet. Now, if we imagine it to be a bar magnet, it's actually produced by rotating currents, etc. But it's like an imaginary bar magnet with its south pole at the top. So the pattern, so since the North Pole of a compass points north, the Earth's magnetic pole, which is geographic north, must actually be magnetically a south pole, as indicated there. Remember that the North Pole of one magnet is attracted to the South Pole of another magnet. So that tells us that that must be how it works, because the North Pole of one magnet is attracted to the South Pole, so the North Pole of compasses is attracted to the South magnetic pole. Nonetheless, Earth Pole in the north is still often called North Magnetic Pole or Geomagnetic North simply because it is north, even though we know the truth. Similarly, the Earth's southern magnetic pole, which is near the geographic South Pole, would be the North Magnetic Pole. The Earth's magnetic poles do not coincide with the geographic poles, which are the Earth's axis of rotation. The North Magnetic Pole, for example, is the Canadian Arctic, which is 1,000 kilometers from true north. So you can see there's a deflection here, right? If this is the North Pole, it's slightly tilted. This difference must be taken into account for accurate use of a compass. The angle difference between the direction of a compass needle, which points to the magnetic north, and the geographic north is called magnetic declination. In the US, it varies from 0 degrees to 20 degrees, depending upon where you are. Okay, on the last page, notice that the Earth in the figure on the previous page in the figure on the right, that the Earth's magnetic field at most locations is not tangent to the Earth's surface. The angle that the Earth's magnetic field makes with the horizontal at any point is referred to as the angle or dip. So you can see here, right here, it's kind of parallel to the Earth, but as we move up, it dips down. So if you're at the North Magnetic Pole, the interesting thing is your compass would just spin around until you tilted it on its side, and they would point straight down into the Earth. So we have the magnetic declination, but you also have the other angle in which it makes with the Earth, the dip. So that dip would be 67 degrees in New York or 55 in Miami. So we have that to consider as well. Lastly here, uniform magnetic field. The simplest magnetic field is one that is uniform. It doesn't change in magnitude or direction from one point to another. A perfectly uniform field over a large area is not easy to produce, but the field between two flat parallel pole pieces of a magnet is nearly uniform if the area of the pole faces is large compared to the separation as shown in the figure right here. At the edges, just like we looked at with electric charges, it would fringe outward like that. So the field fringes out somewhat. The magnetic field lines are no longer quite parallel and uniform. The parallel, evenly spaced fields in the center location, though, indicate that the field is uniform at points not too near the edges, much like the electric fields between two parallel plates as seen earlier. Interestingly, Earth's north magnetic pole has been moving over time on the order of 10 kilometers per year in recent decades. Magnetism in rocks solidified at various times in the past, by radioactive dating can confirm that, suggests that the Earth's magnetic pole have not only moved significantly over geologic time, but have also reversed 400 times in the last 330 million years. So the south became north and vice versa. Also note that the compass gives a false reading if you're standing on a rock containing a magnetic iron ore. So if you have something that's going to, in that small region, overtake the Earth's magnetic field, it could make the compass inaccurate. The same thing as if you take a compass towards a magnet. It won't show you what's happening with the Earth, because in this region here, the barb magnet would be stronger than the Earth's magnetic field. All right, should be able to do the assignment for that. We'll see you again.